Good morning. My name is Ning Lu. I'm from United States, Calabria mine, and it is really my great pleasure to have an opportunity to come to Italy again and to exchange ideas. It has been very impressive by me by two measures. One is the scope of this summer school that people like Ricardo and Giovanna organized. And the second is the extent that where we see that we come from different countries. I looked at the list of yesterday. It comes from 8 different countries. So with about how many people? So it's very impressive. But the most impressive to me is the multidiscipline. And I've been giving lectures about landslide the last decade, many places. Most places I go there, it's very much focused on one subject of the landslide. In my world, it is the physical modeling or physical process of landslide, how it occurs. But landslide is more than just a simple physical process. As we see that people from different disciplines like geomorphology, geology, environmental engineering, geological engineering, civil engineering, you name it. It is very broad because the problem, Mother Nature presents us what we call landslide, require many knowledges. And as we go, we are actually in a very interesting time where we have a different discipline start to converge together. And this is what I feel very exciting. So what we talk about today actually is a field part. It is also become a very exciting time for my personal because Jonathan Godt, Dr. Jonathan Godt, which is with the United States Hydrological Survey, and myself, we just published a book. The book is called Health Slope Hydrology and Stability. So in fact, you can actually, through my today's and tomorrow's discussion, you can learn quite a bit about this book. So this book is here, and I will circulate around each of you. You can spend whatever time you want to look around and then pass over. Eventually, I will give it to Ricardo or give it to Giovanna. I didn't know that. Yeah, so anyway. So as you see, we have tried to put a framework together, which is physical based. What we try to do is not to be too inclusive to the knowledge we feel that it's not directly related to the physical process. But on the other hand, we try to best represent what happened for precipitation-induced landslide, in other words, rainfall-induced landslide. So to be precise, there are two processes, what we call coupled process, occur for landslide. One is the hydrological process, and the other one is the mechanical process. So our book basically is from the framework, as you see that we have divided both into 4 parts. The first one is about the introduction and state of art. As you will see, we actually summarize many of the disciplines that relate to the landslide, and then including the hill slope geomorphology, as well as the hydrology. And the second part will designate for water process, now the hydrological process in hill slope. To understand better, particularly for graduate students, we divide into 2 chapters. One is steady infiltration, the other one is transient infiltration. So the concept of what is a steady state. I mean, Mother Nature, it never occurs steady state, but it is a state that actually helps us to understand when we can remove the time from the picture. But in reality, time is always a factor. So the transient infiltration is the second part of this hydrology. I'm going to talk about that after the first section of this morning. The second part will talk about hydrology. As organizer put me, the first is to talk about next one, which is the effective stress. So the stress concept is the mechanical process. Different than many of the other mechanical processes occur in other disciplines like material science, solid mechanics, structure, engineering, is that soils actually has a long pool of water. Now the stress in soil, it's actually playing a vital role. In many ways we call treatment. Why the landslide will occur after precipitation? It is because the mechanical process is disturbed by the hydrological process. So particularly is how we take care of the stress. This has been, the stress issue has been a long-standing even from soil mechanics or the rock mechanics point of view. It's not so much about the total stress. The total stress concept that we have established is mainly under gravity. Whenever we change the gravity, in this case, it's a unit weight of the material we're concerned, the stress field gradually. But more important, it is the interparticle stress that we attribute due to the water. So we'll talk about that first in this morning's session. And after that, for the book also divide another two parts. One is how we can take care of our material. So under the framework, we have tried to put together our hydromechanical. What are the necessary minimum material properties? Roughly, there are two categories. One is what we call the strength. In other words, every material has strength. Strength is a state of stress, is a limit where you can have the maximum or limit state. So that's the strength. And the second part is what we call hydromechanics. The hydromechanical property is one of the unique about our framework or this book. It's because we unify between the hydrological property and the mechanical property. If you look at the literature right now, there are a lot of people in mechanical and soil mechanics. They actually reinvent the new material property that attributed to water, the strength property, which is unnecessary, as you can see in this book. In fact, that you can all correlate to the hydrological property that we're going to talk about. So that part we're going to discuss tomorrow morning. And then tomorrow afternoon, the final section is to put all those framework, the hydrological process, the mechanical process, and together into the slope stability analysis. The slope stability analysis, again, in this book, we try to divide in two parts. The reason to do so is the first one is the so-called limit analysis, which has been the hallmark of soil and rock mechanics toward engineering application. But that provides us a vehicle to go forward, which is to do the stress field analysis, which allows us not only to look at the slope as one slope, one factor safety, but rather than a field of factor safety. And it provides a way for us to move forward. It's not the end of the story. In fact, it is the beginning of the new journey, in our view, to be more accurate. Because I will talk about it philosophically. What is the current status of the design in geotechnical engineering? And what is the problem? How we can move forward. So the last chapter should provide a way to move forward. And we'll talk about tomorrow early afternoon. So that's pretty much my portion of the contribution. And so I'd like to start now with the first topic, which is deal with the effective stress. So for this part, what we're going to talk about the few items. The first one is to be provide an overview of what people have learned or called Hydrology's effective stress. Hydrology's effective stress is for the saturated across medium, and as well as the Bishop effective stress, which is explicitly developed in the last century, the 50s or last century for unsaturated soil. It has some problem, and that's why in the last 4 years, most people develop a new theory, movement, put aside of Bishop. And we come back to why. So the theory that has been 40 years is around that what we call Coleman's independent stress variable. So give a little bit introduction about that. And then the theory that I've been working on in the last decade is trying to unify the stress concept from Bishop to Hydrology, from saturated to unsaturated. How we can move it together, unified in a sense, also relate to hydrological, completely correlate to the hydrological behavior. In other words, we will show detail. We actually only need to know the hydrological property in order to be able to characterize effective stress and the unified stress concept. And the unified stress concept, very important, is one new terminology I call the suction stress. So suction stress is something that actually I defined about a decade ago. And it is the stress actually in the soil due to water. Now we will talk about that. Finally, give a little bit summary. Now, I prepared this one with the idea that people in this audience does not necessarily know mechanics at all. So you can kind of learn what is the history of mechanics. And the same thing for hydrology. You don't have to have too much background in hydrology. So I just use a few slides to talk about history of mechanics, particularly soil mechanics, and the history the 17th centuries, when the two well-known people, of course, history is always written by the winners, but in this case, Newton, and a little less well-known is Robert Hooke. Robert Hooke actually is well-known for other things like we know the Hooke's law, but actually he also had a contribution to the mechanics. To some degree, historians, particularly in the last couple of decades, people dig out Robert Hooke's diary. They find that actually he's not as bad as what people put in there. Historically, because of Newton prevailed, so it's always a controversy on this figure. But bottom line is what they have been contributed to mechanics, or what is the foundation, is to look at it, in the case of Newton, is look at the amount of force among different body. And the well-known is the Newton's second law is state that whatever the force you have, could be fictitious, could be real, is equal to a mass times acceleration. And Hooke actually independently also worked on what is the relation between the spring constant and displacement, and that gives us the physical force among the different bodies. So that's the beginning of the kind of formation of more become a discipline. Of course, before that, the human also studied mechanics, but at that point it's established as a single discipline. And very important to move beyond the body, the force among the body, is the stress concept. Of course, there are none of the scholars, but with the French scholar, Cauchy is the one that we call continuum mechanics. A lot of work he has been done, of course, he's contributing to more than just continuum mechanics. But the continuum mechanics actually seek a concept go beyond the force. It's the stress. So what is the stress? Stress is the intensity of force. If you consider about the body that we're interested in, within the body, what is the intensity of the force? And that's the stress concept. And that concept is also the foundation of what we today call continuum mechanics. So that is roughly the concept of stress. Of course, along the line that we also concern for human design, the strength of material that we actually try to look at what is the limit of those materials under different kind of stress. So we can define a different criteria, but one well-known, in fact, today in almost virtually all geotechnical engineering design is to use the Moore-Coulomb criteria. And so this particular criteria relates to stress quantity in two simple parameters. It states that the shear strength is equal to cohesion, in other words, internal cohesion, plus additional terms due to the normal stress times the friction angle. So that is whenever material, the state of stress reaches that state. And so in other words, in the shear stress and normal stress space, it reaches a certain line or certain envelope. The material starts to behave very differently than the traditional one we call the linear or nonlinear. The material starts to fail, the phenomenon we call fail. So that's a very brief about the mechanics part. And also, if you look at the interest about engineering, is that there are two things that we are interested from the engineering design point of view, or even from understanding about the nature. One is the stress, to see how the coherence material fail or not. The other one, sometimes the material may not fail, but it displaces. In other words, it actually has deformed under the force, under the stress. So that is something we're interested in. So in order to be able to understand the displacement, we need to know the stress. So the stress-strain relation is well known in what we call generalized, for example, in the most simple form is Hooke's law. It relates the stress and the strain, hence in other words, the two quantity, how you can define it. Now, under the certain kind of strain, how much force or stress is what produced for material. Some material could be stiff, some material could be soft, some material could be ductile, some material could be very brittle. So that is the stress-strain relation. The example is this Hooke's law. So that's pretty much the mechanics up to the single phase. In other words, we have not talked about the water. We only talk about it as a one single phase, either solid, pretty much like the metals and wood. So that is the basically solid mechanics, sometimes we call it. Now let's quickly review the hydrology. So if you look at the hydrology, we all know that if you track back, slightly later than Newton's mechanics. The 19th century is what we well know as Darcy's law. Darcy is, as people here, of course, probably know very well, is a French engineer in a little city called Dijon. He actually conducted experiment. He's an engineer. He conducted experiment for city water. And he did this column test. And the column test actually explicitly looked at how much hydraulic gradient or the pressure differences apply for a column of soil. And then to see how much water he can collect at the end of the tube. From there, he found that there is actually a linear relation between the seepage velocity and the gradient of the pressure. In that case, if we generalize, it's the gradient of the total head. And the proportionality between the two quantities, the gradient and the flux, is what we call a proportionality constant, sometimes called hydraulic conductivity, sometimes called permeability. Of course, it also can be spread into the intrinsic permeability that also relate to the unit weight of water. If you convert the pressure and pressure head and the concept there. So that's one of the study. And then later on, people find that it's not necessarily the pressure gradient that determines whether there is a flow from one point to another point. It actually the energy in a unit of water, it can be stored in a pressure form as well as it can be stored in the potential form. Potential is what we talk about under this case is gravity, the Earth's gravity. So the pressure actually can be spread into two terms. One is what we call the pressure head, the other one is called the elevation head. So in other words, in terms of energy, it's basically stored the two parts, the unit of volume of water. There's energy stored, how much the pressure the unit under, and the other one is how high you put it under the gravity of Earth's gravity. So that's a total head concept. It unifies the entire the field, what we call a potential field. So in other words, for anybody who is concerned about not only the proximity, the concept of pressure head has been established before this, but this is in the proximity. And what's important is also another work in the early of last century is to consider about the transient effect. In other words, the cross-medium we talk about soil and rock. When the water flows into a unit, it not necessarily flow out at the same rate. It actually has a difference. In other words, material, because of the compressibility, because it's in many cases multi-phase, there is a storage effect. So that's what we call the richness equation, which basically is a statement of a continuity requirement. And so that relates to the continuity equation. What those hydrology in terms of the partially saturated soil is concerned, it introduces two very important considerations. So what are those? One is how to define water content. In other words, there is a relation between water content and what we call the matrix suction for each of the soil. So that's a material property. So even in Darcy's law, that in order to be able to define a head, for example, that total head has two parts. The elevation part, which is on top, you can decide by the reference point. But the other part, the pressure under the partial saturated condition, it actually depends on water content. So that is one of the relations. Sometimes we call soil water retention curve. Sometimes we call soil water characteristic curve. So that's one of the material property because each material has their own characteristic determined by the material itself. Not only that, for each material, it also depends on the wetting and drying state. In other words, if we initially were very dry or initially with certain water content, it will be different. And that has a huge implication to landslide problem. Because, for example, the landslide problem very often is like after a kind of dry period. Most of the time, we don't have a rain, right? The rain only occupies, if you get a year or maybe a fraction of a percentage of the time where the sky fall in the water. So during the raining process, most of the soil near the surface in hill slope is under the wetting condition. But when the rain ceases, it starts to it is not immediate dry, it starts by what we call drying process. But the wetting process and drying process, in fact, you will find that it's very different. We're going to learn in today's second section, these characteristics will be different. The other one is how fast the water can move in soil. soil. In the saturated case, we call hydraulic conductivity. In the unsaturated soil, we call hydraulic conductivity, but that's a function of, again, the matrix structure. In other words, it depends on how wet it is. Sometimes you can think about the function of matrix structure, sometimes you can think about it as a function of water content, because the matrix structure and water content can be connected by the first relation. So this inevitably introduces two material property. In fact, these two material properties has been very challenging in terms of how we can categorize that. A little bit later, in the early last century, it started to form a branch of what we call soil mechanics. And what the soil mechanics has been is a traditional, if you look at my first slide, which I started the stress concept in medium mechanics, that's for single cross medium, for only solid. But if you have a solid water, we know that the cross medium has a void. A void could be occupied by water or occupied by air. That's the simplest case. But it also, of course, for the petroleum exploration, it could be another cross medium, another medium like oil. But generally speaking, it's air and water. So how we define stress is use the total stress concept. We know that it will not work. So what's important is defining work is what we call Tazakis effective stress. So what Tazaki said, it's the term effective. What that means? Effective means from our point of view, from human's point of view, we want to see whether the material will fail or not. We want to see how much deformation it is. So to answer the two questions, the stress that it's important, it's not necessarily in the water, it is in the skeleton medium. So that's the essential of the Kazaki's saturated effective stress principle. Now in terms of mathematical form, it's very simple. So what Kazaki stated is that what we need to capture the stress is the skeleton stress. Although the skeleton in proximity you cannot measure directly. But there's two quantities that define that the effectiveness can be measured directly. What are those? One is the total stress. So how you define total stress? So if you have an area, on the area you put a force there, and you divide force by area, it is total stress. So in the case of under the Earth's gravity, it could be a self weight. It also could be a loading. You construct the road, you construct the railway, and then on top of another material, then you can calculate the total stress. So this slide actually, you can even put a sensor there. You can put a sensor behind the retaining wall in the soil. They can measure the spring gauge, give you how much you totally experience, just like spring. So that is measurable. The second part is the water pressure. So under saturated conditions, it is also very easy. You can use so-called piezometer, just directly dip into soil, and then actually give you the number. The number is talk about the pore flow pressure. So that is also measurable. And so with this knowledge, you actually can measure, and you can quantify the effective stress. And that stress has been used for all the geotechnical engineering as well as others disciplines to calculate is a material strong or fail or not, and also how much deformation it is. So that is what the effective stress essentially. Now, moving from the saturated medium to unsaturated cross medium, it has started to become very blurred. First is by what we call a Bischoff effective stress. If you look at the form of the Bischoff effective stress, it actually has a similarity with the Kazaki's effective stress. It has the total stress, in other words, due to the gravity, due to the external loading. But air pressure, because you have the void or the porous, the void space also has air pressure. So the second part is the part actually under a lot of intensive study. What Bischoff figure is equal to the matrix suction, which is the negative pore pressure. It's essentially it's a pore pressure, but it's under negative condition because most of the material proximity above water table, it is negative. So that's what we call matrix suction. You see that directly is the reference of the water pressure with respect to air pressure, and just as with air pressure as a reference. And times a factor. So this is a factor called chi in Greek, and that factor Bischoff defines it. That is a factor between 0 and 1. If your material is saturated, it will be equal to 1. Because if the material is saturated, this one equal to 1, and these two cancel each other, and this reduce back to Kazaki's effective stress. But if for the dry material, the chi is equal to 0. So when the dry material high to zero, this can vanish. So anything you put on your soil or health, it's sustained by your scale. So now everything is effective stress. So that is a Bischoff effective. But there are some controversial and some experiment data, either misinterpreted or some of the problem really with the Bischoff effective stress. One problem I will point out, and this is the main thing that my contribution, and I can point out here is, if you have the soil, when it's dry, just like clay, for example, when it's dry, in fact, it has a lot of internal stress. So if you look at the Bischoff effect just cut to zero, that means there is no internal stress, which is not true. But it's true for sand. For example, if you go to the beach, of course here it's a pebble, it's not a beach. It's not sand beach, but you go to sand beach, and you know that the dry sand does not have any cohesion, but the moist sand has. But for clay, for silt and clay, this is not true. Even though you have it dry, it actually stuck together. So that's one of the missing part of the Bischoff effective stress. So to move forward, we actually come up with the unified effective stress. So the unified effective stress I propose and has been valid in the last decade. It's actually also, you see, very simple. It has the total stress, but instead of using these two products, we assign as a new quantity we call the suction stress. Physically, it is the interparticle stress. So the interparticle stress in the sand case, it depends on saturation. In the clay case, in the silty case, it also depends on saturation. But dependency is quite different. One could be a monotonic, the other one could be non-monotonic, and I'll talk about this. So this becomes a characteristic function. So what we define for the suction stress function, characteristic function. In other words, it depends on the matrix suction. So as you see that, to link these two, we go further. Now we define this quantity, we call the suction stress, which define effective stress, which essentially is the role of the water under the saturation condition to the stress, but also unifying between these two properties. So in other words, we have reached the stage right now, is that if you know the suction stress characteristic function, you can also the characteristic and hydrological function, vice versa. So both ways that we have verified, one is mechanical, the other one is hydrological, but actually they can be defined by the common property. So that's what the status of what we have is basically go back to the connection between these two. As you see that, as I presented, in fact, it is the history in the last half century or so. These two fields, the vapor zone hydrology, soil mechanics, has been developed isolatedly because we've been told to do so by our professors, by our discipline. But in fact, they can be unified, and that's part of the work that we have been trying to attempt is to unify these two disciplines. So now let's talk about some of the detail of the stress issue. If you look at when we said the effective stress, if you look at Kazami's effective stress, it basically say the stress concept you can generalize. The stress concept defined by Cauchy by early time. You can generalize for saturated cross medium by drawing a unit volume, sometimes represent an elementary volume. On that volume, you only put a stress quantity there, in other words, the intensity of force. But you cannot just put the total stress, you also have to put water as an additional stress. And so that water additional stress under the saturated condition, it is compressive. In other words, you have to subtract it from that. So that is the unit of that. And then also accounting for that for a saturated soil cross medium. So this is the saturated Kazami's one. For Bischoff, it said you can put an additional one. The additional one, instead of the compressive, it's a tensile. So it's in the same direction, but if you do this kind of so-called free body diagram, and it's equal to matrix suction times some scale factor. Since that, as I said, that some of the experiment data it was interpreted at the time wrongly indicated that Bischoff effect was not valid. And alternatively, since the 1960s, there are a branch of the people or school of thought pursue the independent stress variable. So what the independent stress variable is quite different than the traditional single stress variable. What the basically says is that we have to define two stress variables. They are not related to each other. So what are those two stress variables? One is the total stress. The other, just like drawing here. The other one is a matrix suction, in our negative forward pressure. So upon that, so it's different than the Bishop says it's a stress has effective. In this theory, basically say we do it independently, so we have to look at a matrix suction as a stress variable. Of course, in the tensile form, it's like that. So in the unit volume, it shows like in the bottom. So that concept has been pushed forward since the 70s. If you look at the literature of soil unsaturated soil mechanics, which is a branch of soil mechanics, from the 60s up to 90s, most of the work development is based on this framework. And until in about 2000, we start to challenge this concept. In other words, let's go back to my first few slides about the stress concept. Is this quantity, in other words, the matrix suction, a stress variable? And that is the beginning of the journey that we find that, in fact, it is not a stress. So I will say something about why it's not stress. So we start with the stress variable that we define is called suction stress. So suction stress is equivalent as if you draw the element in volume, it is a stress quantity. In other words, it's the force divided by unit area. But if you look at careful, the matrix suction itself, it's not. So this stress we call suction stress. I come back later about the matrix suction stuff. But for the suction stress itself, in this case, for unsaturated parts medium, it depends on your saturation, depends on your matrix suction. In other words, the state of the wet and dry. And so we can ask ourselves a couple of questions. One is it effective in describing strength and deformation? So that's very important because all our concern as far as our human to the natural material is going to fail, and how much it's going to deform, even though they are not fail. So the second question is how we determine that, because you can develop a theory, and many people have been attempting and continue to do so. The go back is, can you categorize that? Can you measure that, or can you quantify it in a very simple way, in a way that most engineers or most technical people can use it? And that is a big important challenge and questions. Now let's look at about the issue why I make the statement say matrix suction is not a stress variable. Here, this diagram actually shows clearly that why the matrix suction is not a stress variable. Let's first look at what's the air pressure. If you have a cross medium, of course, in the air is occupied 100% by like nitrogen, oxygen. So the air pressure is basically a thermodynamic energy state of volume of the air. But if you go to the cross medium, so that you have a solid air and a water, three phase of the material. But if you zoom into the air phase, the air pressure is still valid. In other words, the air pressure is a stress of the air, the unit area of the air, inside the air. By the same token, that you can also, but if you look at the volume of what we are interested, it is air pressure actually, it's not a magnetic, because in total one you have to divide by the entire area, which has a solid and water. It's not a stress that we are concerned. By the same token, the pore water pressure. So pore water pressure is defined at a much smaller scale. If you use a continuum mechanics concept, it's defined in the pores. Of course, if you have a saturated medium, then you don't need to. The scale could be very large. It's not that it's because all the void are occupied by water. But in this case, under partially saturated condition, you have to look at the scale effect that is important. So it is a stress when you go into the little menisci or into the soil water. But it is not a stress when you look at the entire top volume, because the total force integrated divided by area in that case is not equal to the quantity of the pressure. So matrix suction, what is it? It is by definition is the differences between the air and the water pressure. So it's a stress variable only at the porous scale, but not at the representative elementary scale. The representative elementary scale is the one that we deal with the material. We consider about a point. If you say, I'm talking about a point in the hair slope, that particular point will in fact including 3 phases. It's at the representative elementary volume scale. So in other words, it is what we can use as a stress quantity. And a little bit more careful, more quantitative representation of our distribution, this concept is, you can think about the draw represent elementary volume. In this case, I draw about tens of particles, sufficient to define a point as what we call use as a stress. If you do so, you will find that the contribution of air pressure, which is established at the pore air scale, has to be upscale, has to times the area where there is air. And by the same token, the water pressure too. The water pressure depends on the saturation, but you have to integrate times the area where the water is acting. And so if you do so, you will find that the matrix suction is not, but the quantity that actually really represent the stress through the represent elementary volume is what we call the suction stress. So that's where the suction stress comes from. It has the components due to the negative water pressure related to the saturation. It also has to do with the surface tension. Surface tension has been considered in many of the conceptual model, which basically is due to the stress or the force at the interface of water air. It also has to do with one of the very important quantity, what we call the physical chemical force. So what is the physical chemical force? The physical chemical force is something that you don't have a lot in sand, you have a lot in silt and clay. It's basically from what we call a van der Waals attraction. Van der Waals attraction is at the atomic scale because the asymmetry of the electromagnetic field it causes attractive force. So van der Waals attraction is one of the very important physical chemicals, as well as what we call double layer. Double layer is again formed because the clay mineral. You have this water that actually can form the cation layers, and that will be called double layer. Because of the existence of double layer, they can have an additional attractive or repulsive, in most cases repulsive force among the particles. So the net of these 3 origins, as we understand, is what I call suction stress. And I can explain this a little bit more by looking at the issue of the quantity individually. But if you lump these, all those, into the scale of what we call the representative elementary scale, the scale that we can define stress, and you will find the suction stress is a stress variable. Then after that, you can use the same parallel to the traditional classical total stress. But you cannot use a matrix suction because it requires upscale before you can put it into the elementary volume to be parallel to the external stress like total stress. So that is one of the very fundamental and basic concepts that we talk about here. So let me explain what are the sources of those what I call the physical, chemical, and how they depend on different kind of material. You can think about it depend on there are 2 controls. One is what kind of material you have. In other words, whether you have a clay mineral, whether you have a silty soil, or whether you have a sandy like quartz. The other one is depend on how much water you have, because once you have water, those force or stress interparticle level is going to be different. Specifically, you can look at the plot of first diagram, which is the interparticle stress versus the particle size. And as you see, graphically, the sandy size, the silty size, and the clay size. And there's a lot of correlation if you study mineralogy of rock and soil. You find that there is a correlation because of Mother Nature's process between the different mineral and the size. So in other words, you go to the beach, the fact that you find a lot of silicon oxide, or we call sand, it's by no coincidence. It's because those materials are very resistant to weathering, and eventually the other material just be turned into clay or silt and settle on the bottom of the ocean. So there's a correlation. So you look at the correlation and you find, for example, the van der Waals attraction. So the attractive force, I use a dashed line, depends on particle size.
Virtually, you can ignore manual depth attraction. You look at this micrometer. If it's 10 micrometer and above particle, the manual attraction almost negligible, and that's why the sand does not have manual attraction, or virtually none. And then, but it will increase as your particle becomes smaller and smaller, and it increases up to several hundred kPa when they become really, really fine material. If you look at the capillary attraction, it's similar. Capillary attraction is determined by the meniscus readings. If you look at the Kelvin's law. But so the smaller the particle size, the smaller pore size is going to promote. Therefore, the higher the capillary stress is. And on the other hand, if you look at double layer. The double layer is also similar, depending on the particle size. When you have clay, you have a lot of clayey particle, a lot of surface area, it promotes a double layer. When you have a silty or even sand, you don't have any or virtually none double layer. And so those are how they depend on the particle size or mineralogy. The other important part is how they depend on saturation. And that is actually start to become complicated. For example, if you look at the capillary attractions, and now due to the interface of air and water, when you have a zero saturation, because you don't have an interface, so you don't have a substantiation, so there's no attractive capillary force. On the other hand, when you have a saturated, you also don't have an air water interface, you become zero too. So somewhere between that, they can reach the maximum. And that is very well illustrated in sand. So if you want to build a sand castle, you cannot, you have to put water into certain amount of water content. That depends on the particle size too. And then you actually can reach the maximum capillary stress that can build a nice sand castle. If you look at the manual attraction is most strong when the soil is dry. Why? Because when you have a solid-to-solid contact, the manual attraction, which is capillary constant, is the highest. But when you start to have a hydrate, so you have a contact with basically solid water and then maybe more water and then solid, the manual attraction is going to decrease. But it's not going to decrease to zero, it's going to decrease to some magnitudes. So that is the manual attraction nature. And that is why when you have a saturated soil, you have a cohesion. Clay, you have a cohesion. And where that cohesion comes from? That cohesion mainly comes from these manual attractions. But as the clay dry, the manual attraction becomes strong because it promotes more and more solid contact. And so that is the dependency of that. And that can also up to a few hundred kPa. And that's the order of magnitude. And then if you look at the double layer revulsion, it's the other way. In other words, double layer revulsion only form when you have a lot of water. Saturated is the highest one. And it also depends on the pore chemistry. Whether you have a high concentration of salt or low concentration of salt, it will actually change the influence of the double layer. So that is the dependency of these things. It makes this interparticle stress. Some will complicate because it's a combination of these two findings. One is repulsive, the other one is attractive. So they become net of that is what I call the suction stress. So that is the origin of the suction stress. If you put this, all these things stress together, what you find is this diagram. It shows that interparticle stress depends on the saturation, depends on what kind of material you have. For sandy material, you have this increase-decrease. It reaches the maximum at about few kPa of all the magnitude. So few kPa is somewhere optimum for you to build a sand castle in a meter or two. You cannot build a sand castle higher than 2 meters. Why? It's because the size or pore size of the depending on particle size of sand is at the millimeter scale or sub-millimeter. The sub-millimeter, because of sand, you don't have the physical-chemical force. In that case, you can only have the capillary force, and the capillary force can only maintain that much, a few kPa. So a few kPa, it will convert. A few kPa of stress interparticle, it can convert to shear resistance. I will talk about later on about the 10 kPa, and that will be able to sustain a couple meters of sand castles. And the silty soil is different. Silty soil, we know that many parts of the world they have what we call loops, which is basically formed geologically under the eolian or the wind. The wind blows lots of sand, but come with a very some feel of the fine material, like clay material, and that provides an excellent interparticle cementation. Sometimes we call, or basically it's the attractive force with the physical chemical. And that's why you can see in the desert area, you can see a low slope. It can stand up to tens, even 100 meters of nearly vertical. It's we talk about a lot about creek. But it's under those suction stress, which could be a tens of kPa. Sometimes it could be up to 100 kPa. There are other kPa that will be able to sustain that height of the slope. Now, look at the clay. Clay is very different. Clay no longer becomes an increase-decrease. It's actually a monotonically increase is attractive. The saturated case has the smallest one, which is actually can be related to what we call apparent cohesion. So I mentioned the more critical criteria, the two parameters, cohesion and the friction angle. The cohesion, where the cohesion comes from? Why sand does not become cohesion? Why clay has cohesion? It is due to the saturated physical chemical force of clay. But as you dry the material of clay, it actually becomes stronger and stronger. In fact, if you do the experiment without letting the clay to crack, by the time you dry under the sun, it will become like a clay pot. It's very strong. It could be up several hundred kPa magnitude of the attractive force. So that is the stress, the interparticle stress that we form, what we call the suction stress. So suction stress concept from these three, in a way that basically is either a function of saturation or it's a function of matrix suction. So the magnitude also changes. In other words, we relate to the slope, stability, and this plays a very important role. For example, if you have a silty soil, from the case of the dry, they can have a few tens of kPa. But if you have heavy rain, that tens of kPa of stress can disappear almost instantaneously because of this reduction of this saturation from dry state to completely saturated state. This part will completely reduced. And they can, so sometimes in some area people call collapsing soil. It's not collapsible, but upon the weather, because it forms under semi-desert area. But when the human start to live in those areas, they like to put water, irrigated water to those soils, or do gardening, and so it starts to collapse. And because of the disappearance of these tens of kPa. Now, to quantify that, go further, what is the suction stress? And in fact, the suction stress you can characterize by the shear strength test. So on the left, it shows that up to now, there are a lot of tests that have been done for material partially saturated soils. Now, what they find is if you have a saturated soil, they behave like this. But then if you have unsaturated, they actually go up, depending on matrix suction. The stress, the classical interpretation is the stress, the cohesion increase as the soil becomes dry. But where the cohesion comes from, so this is one of the key in my theory. Is if you look at this diagram, the cohesion here is actually it's a shear stress because it's a conception of vertical axis. So it's a stress in the form, not a normal stress, but in the shear stress. But where does it come from? It comes from, if you do a projection, go back to zero, those points. Those point is a point, it's what I call suction stress. It's a point that it's not a zero, it's a zero shear stress, but it has a definitely magnitude of a tensile or interparticle stress. And so that's why if you have a sandy material, you don't have a cohesion, so therefore you don't have a suction stress. But when the material becomes more due to the physical chemical, due to the saturated soil nature, it actually increases the more negative. So that is the origin. So the traditional, what we call the apparent cohesion, in fact, is a function. It comes from this isotopic. Or in a simple way, just think about a particle of material will increase the cementation, just like a cement. But that cement depends on two categories of property. One depends on what kind of material you have, whether it's a clay, whether it's a silk. The other one depends on how much water you mix them. If you put a lot of water, it will be different than a little bit of water. So that two things basically control the magnitude. So conceptually, I draw this one. If I draw here, it's more a little more clear. So suction stress is vertical axis, and horizontal is a matrix suction. When you have this become a negative matrix suction, which is forward pressure, so it's a one-to-one relation between the forward pressure and suction stress, and that's what in the picture in the consumption effective stress. But when you become unsaturated, even though you are actually under above water table, you can be a negative before the soil start to desaturate. Sometimes we call this point called air entry value. Below the air entry value is still one-to-one relation. Above the air entry value, because soil start to desaturate, so you no longer can trigger matrix suction or water pressure as a stress value. And you use the suction stress, it actually changes, depending on what kind of soil you have. You can go to a 0 for sand, you can go to the asymptotic sum value for clay. So the key is to characterize this suction stress. And not only to characterize that in the mechanical way, which I show you here, you can do a shear strength test, but also characterize it in hydraulic way. Now, how you can relate to the soil retention, for example. So that's the important thing. And is this concept of suction stress valid? So that's what we show here. I use many of the other people's experiment data. So the conductor shear strength test. This is the you can look at the horizontal axis different way. One is a total stress. So people conduct the experiment under different matrix suction. You see the hollow and different matrix suction, the stress is different. But if you use the suction stress concept, find out the suction stress for each corresponding matrix suction, and you use the effective stress and put it as a horizontal, you find that it actually follows one line, which is a validation of the suction stress concept or the effective stress. But the effective, in this case, extend from saturated to unsaturated, using the suction stress to replace the forward pressure. And each of those experiment different envelope. If you put a projection there, you can put a projection in the vertical way. So that is how they depend on matrix suction, or another suction stress depend on matrix suction. You start with the saturated, the one-to-one relation between suction and matrix suction and suction stress. At some point, you start to desaturate soil, and it actually bend, becomes smaller and smaller instead of go to this 45-degree one-to-one relation. So that is the suction stress characteristic functions. And this experiment data indicated that the concept of unified visit is valid. And this is another soil called compacted soil, which basically you prepare in the laboratory. As you see, again, if you use the total stress concept, it's not a one-faded envelope. But if you use the effective stress, it can be effectively put into one envelope. So again, the corresponding suction stress it indicates the validity of. And this is another example for glacier tilt, which basically is a silty material under the geological process of glaciation. And you see that again, the hollow line indicated under different saturation, using a total stress, using independent stress variable. But you use a suction stress, effective stress, it's all unified to one line. So these are the stored indication of the proposed suction stress and the validation of it. Now I will explain a little bit about the meaning of the suction stress. So if you look at this diagram, this diagram will show the vertical on the left is matrix suction, on the right is suction stress, horizontal is saturation, or called effective saturation. So this line, when you look at the left, is what we call soil water characteristic curve. And the theory will be formulated, as I mentioned, that in fact you can completely correlate it between soil water retention and suction stress. So what is that suction stress physically, or we use called energy concept? So if you look at the soil water retention at any point, just look at this point. What is the meaning? It indicates at the particular water content how much energy in terms of pressure that you have. So that is exactly the meaning of a matrix suction. But if you look at the area under this one, in other words, it is the matrix suction times the degree of saturation. That's how much energy in the one unit of unsaturated soil. In the soil water, in the water. So that's exactly what we define called suction stress. So we can define this second curve for suction stress characteristic curve. No more, no letter. Just use this less. Just use this area under the solver, each point under the solver detention. So just dot product of that. So that's the exact meaning. So interpretation is the negative polar pressure in the blue sky. All the energy is going to convert to make your stress at the represented elementary body. So that's the meaning of the suction stress. So what is the matrix suction, as well as define, and what is suction stress? The difference is matrix suction precisely is the mechanical energy in soil water per unit volume of soil. So that is the meaning of matrix suction or negative water pressure. Now, what is matrix suction stress? Suction stress is the mechanical energy in soil water per unit volume of soil. So in other words, it just upscale that from little tiny menisci into the volume. Roughly it is these areas under the soil water retention for each point, which form the second function. So by doing that, actually, if you know the soil water retention, you know your effective stress, because this is internally correlated. Vice versa, if you know the suction stress, you can know the soil water retention. And we specifically give example of the specific form. For example, if you use one of the widely used bank-Newton's soil water characteristic curve, which is well established in vegetal hydrology, you can look at you can form the suction stress as a function of saturation. And graphically, you can plot left is the matrix soil water characteristic curve, right is the suction stress for different soils. The difference is, as you see, that those are monotonic function. Here, the interparticle stress, it really depends on what kind of material you have. It could be a non-monotonic, it could be a monotonic, as well as the order magnitude, depending on what kind of mineral and saturation you have. And you can also plot that instead of a degree of saturation, you plot it as a matrix suction. Sand is increased and drastically reduced. Silt increase and gradually reduce. And the clay, it just go all the way increase. What's the beauty about this is all those complex form in the particle is in the one same mathematical form with the two parameters. And that two parameters also define the soil water characteristic curve. So that is the state of theory. And here is just some of the validation. So if somebody measure the soil water retention and conduct the shear stress, you can basically reduce the soil water retention curve to predict their shear stress behavior that come down to the suction stress characteristic curve. It's just an experiment validation to show that they are valid. This is a different material for sand. So basically, that's basically the first section. I will just use a few slides to give a little bit of extrapolation and say, okay, now we talk about suction stress or unified effect stress. The stress is soil skeleton for partially saturated material or variable saturated, which including saturated and saturated. Can you imagine what happened in hill slope? So I just use the results as kind of illustrator. You can imagine the interparticle in the hill slope. Depend on the depth, and in this case, we just use a steady state case. And so the steady profile, which means there is no prime effect. And we actually will talk about hydrologically after the break. But the form, the hydrologically, I'll start with here. There is the saturation. We have formulated a simple analytical solution, which is categorized depending on how far away from the water table. You can have the material, the Z, which is above water table. The saturation depends on the flux. So P is depending on how much steady flux is going into the soil. And what is the saturated conductivity? And what is the parameter? We call M parameters that relate to the foresight distribution and the beta parameters. So you can know the profile depending on infiltration, or it could be evaporation. So this Q could be a positive and negative depending on the after rain it could be evaporated. So you can if you use steady state, you can use a different Q value. And same thing for the matrix suction of water pressure above water table. The suction stress concept is very simple now because it just basically based on the theory, it's the energy in the volume of the soil. So that's equal to this profile times this profile, it becomes this profile. So back and forth, because it looks a little bit complicated, but if you read the program papers, then you can come up pretty simple. Here is an illustration of the, let's say you have 2 meters of sand layer. So here is the water table, 2 meters above water table to the ground surface. And we can look at how much, in that case, versus the water content. How much water content depends on the infiltration. Hydrostatic, which means no infiltration, and that's the solid line. And if you have an infiltration, and then it's this line, the matrix suction and the water content will not increase compared to hydrostatic. And if you have an evaporation, it goes the other way. And what is the matrix suction of water content? What is the matrix suction of water potential? And we will talk about this one after the break. This is the hydraulic part. But once you have that, you can know the suction stress. So here's what you think about the suction stress. Just look at this profile. The other profile will do very quickly. But look at this profile. What that says is, at the water table for this sandy material, you do not have any cohesive force. Right? Above water table, and you start to increase. And at some point, actually, it had reached a maximum and start to decrease a little bit. And that also depends on your infiltration or evaporation. But in the case of sand, it's not so much effect. In other material, as I will show you, so this is like a silky material. You see that the suction stress actually varies quite a bit depending on how far away from them. So, for example, the infiltration will promote less suction stress. So, in other words, less stable. Because the suction stress, you pay attention to the negative sign, even though this is positive, just for the graphical purpose. It actually, the more negative means the more put a particle together, which means the higher effective stress, which means strong. So that is a general kind of pattern for sand. Now give another example of clay. So you see the clay, it actually varies a lot in terms of how the infiltration is going to be affected. And of course, there's some of the multi-layer. I think this material, because you will have fun in particular in the book. Multi-layer behavior is much more complex, but we can also use this framework. And depending on what you have, the example here is a sand clay. Now the top is a sand, bottom is a clay. And you can have all sorts of scenarios, and I won't go through that detail. And you can study it. And then another example is a transient. So we can also use what happens if we have a sudden rain, for example, like this. Time versus the head at the surface. In other words, if it rain on the top of the surface, and let's say the head becomes 0 for a certain time, and then stop. And if you have that kind of scenario, what happens after the rain stop, or even during the rain stop, is the water start to percolate down. So the water start to percolate down, you can actually look at this arriving time of the wetting front. So the horizontal is the arrival time. The vertical axis is the distance, the water gradually go down. And that depends on what kind of material. Some material will be faster than other material. For example, sand. Sand can go very fast, go down, and then the clay will be slow. And so that process to see what is the suction stress. The water content, this is transient example we're going to talk about after break. And you can see the suction stress correspondingly depend on. Originally, at the time it was 0, you have sustainable suction stress, as I showed you in the previous case. But once it starts to infiltrate, the suction stress disappears. And because as the time goes, the wetting goes progressively, and then the suction stress gradually goes down. So this is very illustrative because if you have a layer of slope, even if the suction stress is reduced in such fashion, which is somewhat simplified, but then disappear of that at some point, at a certain depth, you can cause the shear stress to reach the failure criteria. And that is why, in many cases, we know that it's at the interface of bedrock with the soil where it's most vulnerable. But that's not always true. In some cases, the failure occurs within the unsaturated zone or within the soil layer. And how you explain that one? And this is one way to explain it. So basically with that, this is just a different kind of a scenario, different kind of soil, and you can see that. I'd like to make a few points before we take a first break. First one is a stress variable effectively describes two things. One stress, one deformation is presented in the suction stress characteristic function form in this framework. The second point is what is the suction stress characteristic is actually expand Kazaki's effective stress into unsaturated condition. And actually, also we consider, we don't think about the really man will. We think it extends Bishop effective test, as well as two independent stress variable for all solids under variable or unstable condition. The third point is, as we show, as well as you can see the literature, this theory has been valid against the experiment data. The experiment data not only for the shear strength, but also for hydraulic tests, even for deformation tests. And this is also even correlate. That's a very important point. In other words, the suction stress, you will be able to characterize the stress or effective stress for partially saturated material. You can know that from the solvent retention. Because interparticle stress, fundamentally, I've been looking at this topic of different phenomena in porous medium with some of my colleagues. Essentially, we all agree, what are the control? For example, if you're concerned about reciprocity, if you're concerned about the diffusivity, of chemical or water, what is really controlled, or in this case the stress, is the pore size, as well as the medium that you involve, the quality at the interface, the quality interface of air, water, interface of solid and water. So those are the intrinsic property, plus the pore size distribution. So that's basically the promise, the way you can actually unveil the different phenomenon, the flow phenomenon, the chemical contaminant transport phenomenon, the heat transfer, as well as the electrical field. In porous media, you can actually use the same kind of common property. In this case, is the pore size and the innovation property. And as you see, the dynamic of suction stress in the field, in the last few slides, I showed that it could be fully determined once we know how the water is going to transport in porous media, which I will talk about it after the break. And generally, the wetting process, if you have some point you can get away without doing quantitative reason, the wetting process generally will diminish the suction stress. In other words, it will make the effective smaller. That's generally speaking. And it will result in a smaller effective stress and promoting failure material. And that is the explanation by the effective stress framework I present today in this morning. Thank you very much. I think we should take a break.